Okay, today we're going to talk about section 5.5. When we talk about the zeros of a polynomial, this is also known as the roots or the solutions to the polynomial. We'll just let our polynomial be some f of x, and when we set it equal to 0, we'll find solutions or the roots or the values of x which make it 0. So all of these things, these are three ways to talk about the solutions to when we let the polynomial function equal 0. Okay, let's remember, let's do long division. So let's say we have some polynomial, we'll call it p of x, 2x cubed minus 5x squared plus 4x minus 6. And we'd want to divide this by x minus 3. Alright, so we'll set it up, x minus 3. These are all in descending order and everything's represented, so we don't have to put in a placeholder. Okay. So first we begin by asking how many times does x go into 2x cubed. So really we're just reducing this to get 2x squared. We write that up top. Then we have to multiply that by this to get 2x cubed minus 6x squared. So that's what gets written here. And then we're going to subtract. And remember, when we're subtracting, we are changing the signs. So now this will go to 0, and minus 5 plus 6 is x squared. And then we can bring down the rest of the polynomial. And then we can start again. This time we'll ask how many times x goes into x squared. And that simply reduces to x. Okay, it's positive, so that becomes a plus x up top. Then we take this times this. So x times x minus 3 is x squared minus 3x. And that's what we write here. But we're subtracting, so we want to change the signs. Now this will go to 0. This is 7x. And we bring down the minus 6. Let's see, where can we do that? Then we ask how many times x goes into 7x. And that just reduces to positive 7. Okay, so that's a plus 7. Then we take 7 times this, which is 7x minus 21. So that's what we write here. But we're subtracting, so we'll change the signs. Now this will go to 0, and positive 21 minus 6 is 15. Okay, so we have a remainder of 15. Alright, which means we could write this division problem like so. We could write it as our original polynomial, 2x cubed minus 5x squared plus 4x minus 6. Remember, we divided that by x minus 3. Okay. So we found out from here that it goes in a complete 2x squared plus x plus 7 times. This is what's known as the quotient. But we had a remainder, and that remainder was 15, but it was 15 over x minus 3. Okay. This is the remainder. And this was the divisor. That is what we were dividing by. Okay. So now, looking at that, let's continue and look at this example. We'll take our same polynomial up here. Let's say our polynomial is the same one, 2x cubed minus 5x squared plus 4x minus 6. And what I would like to do now is just do a basic evaluating. Let's evaluate this polynomial at 3. So that'll be 2 times 3 cubed minus 5 times 3 squared plus 4 times 3 minus 6. And I will give you a minute to do that. Okay, so 54 minus 45 is 9. 12 minus 6 is 6. And 9 and 6 are 15. So let's look again at our above example and see what happened here. Okay. What are the similarities from our division problem that show up here when we evaluate P of 3? Well, one thing we can notice is that we have the number 15 here as an answer, and 15 was also the remainder. Another thing we could notice is here we put in a number 3, and what we were dividing by was x minus 3. And this is always going to be the case if we're in this type of division problem. Okay. So here I have a linear divisor. I'm taking x with no coefficient in front and then just subtracting a constant. So this is linear. Okay. Coefficient of 1. Okay, so that leads us to the remainder theorem. So a theorem, I'm just going to abbreviate THM. A theorem is something that's true, that's already been proven. So we don't have to go back through and prove it. We can just use the result. So let's say we have a polynomial. So if some P of x, a polynomial, is divided by x minus a constant, then the remainder will be the polynomial evaluated at this constant. Okay. So why is this going to be helpful for us? I mean, it only tells us what the remainder is, and that may not be helpful. But it is helpful in one specific case. Let's remember that, like, if I had to take 7 and divide it into 35, I would say the answer is 5. 5 times 7 is 35, and the remainder is 0. That's because 7 is a factor of 35. So where the remainder theorem becomes very helpful is when we're looking at the factor theorem. So the factor theorem says this. Let's see any constant be a factor or a zero is another way to say it, or a root or a solution, okay, of a function f of x. If this is true, I'm going to use this symbol. This means if and only if. I'll explain it in just one moment. Let C be a factor or a zero of a function. Okay. Then x minus C let's see. I'm sorry. This shouldn't say factor. Let C be a zero. Okay, so it's a solution. So if we take f of x and we set it equal to 0, then we would get x is equal to c. So whatever that c is a zero of the function, if and only if x minus c is a factor of the function f of x. Okay. Okay. So what is that saying? Well, once we have some solution, let me just give you an example. Okay. All right. For example, okay. Let's look at, first of all, let's show that x plus 2 is a factor of, let's let our function be f of x is x cubed minus 6x squared minus x plus 30. Okay. I also said I was going to explain this if and only if. Okay. So if c is a zero of this function, then x minus c is a factor. We can just get that directly. Or if we find out that x minus c is a factor of the function, then we can automatically say c will solve this equation, okay, where the function equals 0. Okay. So how are we going to show that x plus 2 is a factor of this? Well, if we use the remainder theorem, okay, and we take the polynomial and evaluate it, now if we get a remainder of 0, then x plus 2 would be a factor. Now the thing we have to be careful about, though, is the way the theorem is written is it has to be x minus some constant. Okay? And what we have here is a plus, so we need to rewrite this as x minus a minus 2. So minus 2 is what we need to be putting into our function. Okay? So now let's check that. Okay? So minus 2, minus 2, minus 2. Okay? Now, negative 2 cubed is negative 8. And we have minus 6 times negative 2 squared is positive 4. A minus and a minus became plus. And then 30. So negative 8 minus 24 plus 2 plus 30. Okay. Well, this is negative 32. And this is positive 32. Okay. 8 minus 24 is negative 32. 2 plus 30 is positive 32. And this equals 0. So what we have shown then, so we can say then that x plus 2 is a factor of f of x. Okay. And so that was much easier to do, to show that x plus 2 is a factor, by evaluating our constant and showing that it equals 0, rather than having to go through the long division of dividing x plus 2 into this. Okay. But this is a third root, okay, so that means I should have 3 zeros to this equation. So let's try and solve that and see what happens. Okay, so we're going to solve f of x equal to x cubed minus 6x squared minus x plus 30. where does that equal 0? Now, with our regular techniques that we have, we would try, up until this point, we would try and do a factoring by grouping, because there isn't a greatest common factor at all. I could factor an x out of here and get an x squared, or an x squared and get an x minus 6, but there's nothing for me to factor here. So what are we supposed to do? Well, I know that x plus 2 is a factor. So let's do the long division so you can see it happen. Okay, we know it's going to be a factor, but I don't know what that quotient is. So x plus 2 goes into x cubed minus 6x squared minus x plus 30. Okay. So here we go. X goes into x cubed, x squared times x is x cubed. 2 times x squared is 2x squared. But we're subtracting, so we'll change the signs. Okay, this goes to 0, minus 8x squared, and we'll bring down the rest. Now, we'll look how many times does x go into negative 8x squared. Well, that's a negative 8x times. Okay. Now this times this is negative 8x squared minus 8 is 16x. Okay. But we're subtracting, so we'll change the signs. Negative 8 plus 8 is 0, minus 1 plus 16 is 15x. And we bring down the 30. Okay. And lastly, we'll ask how many times does x go into 15x. That's a positive 15 times. Okay. Take this times this to get 15x plus 30. Okay. But we're subtracting, so we'll change the signs. And now, when we subtract, this will go to 0 and this will go to 0. Which we knew that was going to happen. What we didn't know was this quotient up here. Okay. So what does that mean? Well, what that means is that I can rewrite this function, f of x, as the divisor times the quotient. Okay, so this is one factored form. I had no one factor. Right? But we also know it's a third degree equation, so we need 3 solutions. So let's see now that I've found one factor, if this won't factor, and this will factor into x minus 3, x minus 5. So now, if we're trying to solve f of x is equal to 0, well, it's just a matter of looking at it in the factored form, x plus 2, x minus 3, x minus 5. Okay. Now, if 3 things are being multiplied together and they equal 0, it's either the first equals 0, the second equals 0, or the third equals 0. Okay. So either x is equal to negative 2, aha, there's the c we were talking about, or x is equal to 3, or x is equal to 5. So sometimes the factor theorem is going to be very, very helpful for us to find out where zeros occur. And then maybe what the remaining is left would be very easy for us, especially if it's quadratic, we'll always be able to solve it. It may not factor. It might not even be that these are real roots. They could be imaginary. They could be irrational. But we will be able to find them if the remainder, or if the quotient is a second degree. Okay. Now, there's another theorem in here called the rational zeros theorem. So I want to give you an example as to what a rational zero is to begin with. Okay. Remember, rational numbers are those that can be written as fractions. Okay, so for example, let's find the zeros of our polynomial, which is 6x squared minus x minus 35. Okay. So if we want to find the zeros, we have to solve where the polynomial is equal to 0, or find the solutions to this equation. Okay. Now, it turns out this one's going to factor. Okay. This will factor into 2x minus 5 and 3x plus 7. Remember that the 2 and the 3 come from the 6, and the 5 and the 7 come from the 35. Okay. So now, when I split these apart, I have 2x minus 5 equals 0, or 3x plus 7 equals 0. So it's either that 2x is equal to 5, or x is equal to 5 halves. And here we'll have 3x is equal to negative 7, so that x is equal to negative 7 thirds. But notice what happened when I did that. The 2 and the 3 are represented here, and the 5 and the 7 are represented up top here. So that is, these are fractional answers, and these are rational zeros. So we have a theorem about that, okay? So let's write that down. All right. So this is the rational zeros theorem. Okay. So let's say we have a polynomial. Okay. So if our polynomial, now remember we can write polynomials in this descending form of a sub n x to the n plus a sub n minus 1 x to the n minus 1. So remember we're in descending powers. And it'll keep going and going and going until finally we get down to a sub 2x squared plus a sub 1x to the first plus a sub 0. Okay. If we just have this portion of it, then it's quadratic. Okay, but it can be as large of a degree as we need. Okay, so let's say we have this polynomial, and we have to know this. And if x is equal to p over q, okay, that is, if this is a fraction or is a rational zero of our polynomial, okay, then what can we say? Well, we can say this. Then that from here, okay, let's look again from here before I tell you this. Okay, notice that the numerators here were factors of the constant term. Then this p, okay, then p is a factor of the constant term a sub 0, okay, a constant. Okay. Then this p that we're talking about here is a factor of a sub 0, which is our constant term. That happened up top here. That's what I was showing. Our numerators here were the factors of 35. Okay. On the other hand, then q that we're talking about here, the denominator, then q is a factor of a sub n. Okay, so the leading coefficient. Okay, so what does that mean? Let's look at an example so we can see. Alright, now it doesn't guarantee that we're going to, that they actually will be zeros, but here are the possible. Let's find the possible rational zeros to f of x is equal to 3x to the fourth plus 5x cubed minus 7x squared plus 6x minus 6. Okay. We do not have any techniques at all. If we wanted to find the zeros of this by setting it equal to 0, we don't have any techniques that will help us solve this. We can't factor it. There's not a u substitution. There's just no way that we have it. So this is where the rational zeros will come in. Okay. So I'm thinking, well, what could we do? Well, then, if there's a rational zero, it will have to take the form p over q, right? Okay. Where p is going to be a factor of -6, and q is going to be the factors of the leading, which is 3. Okay? All right, now we're going to get a nice list. Okay? So, what that means is that we're going to have a set of numbers. Okay? So let's write these out and then simplify it. Now, the important thing to recognize here, well, I'm going to explain this in just a minute. Okay. All right, the factors of 6 are 1 and 6, 2, and 3. Okay, so I have 4 possible numbers that go up top. And the factors of 3 are 1 and 3. Okay. Now, the plus or minus is going to come in because of multiplication. Okay. So, it could be then, let's reduce this set. It could be that the factor could be plus or minus 1 over 1, which is just 1. Okay. 2 over 1, which is just 2. 3 over 1, which is 3. And 6 over 1, which is 6. Okay. So that's just from the first division. Okay. This is dividing. Okay. Now, it could also be that they could be 1/3, 2/3, 3/3. Well, 3/3 is 1, so we already have that. Or 6/3, and 6/3 is 2, so we already have that listed. Okay. Now, if you don't write it in set notation, you need the plus or minus in front of every single one. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/3, and plus or minus 2/3. So that means that this, if this polynomial that we were given has a solution that is a rational number, these are the options that will be. Now, it doesn't necessarily mean that one of them will be, but these are the possibles. So there's 2, 4, 6, 8, 10, 12. There's 12 possible rational zeros to this equation. And we could go about then testing them. Okay. That is, we could plug each of these in to find out if they equal 0. We could test f of 1 and run it out. F of -1 and run it out. F of +2 and run it out. Okay. Now remember, when we're doing this, we're not actually going to know what the quotient is. So this, if 1 is a factor, then x, let's see, if +1 is a factor, then x minus 1 is, I'm sorry, +1 is a solution, then x minus 1 is a factor to this. which means when I do the long division, I would have a quotient that's going to be a third degree because this one's a fourth. So it's not necessarily the easiest way to go about finding your rational zeros by plugging them back in. Okay. Now, we're going to take a different example where I show you a different way that will make it easier. Instead of plugging in all the zeros and not knowing what the quotient is, we could use synthetic division. So let's do that in our next example. Okay. So if f of x is equal to 4x cubed minus 3x minus 1. Okay. We still don't, to find the solutions, we'd have to set it equal to 0, and we still don't have a way to solve this. Okay? So let's resort to the rational zeros theorem and say that x will be equal to this, if it's rational, some p over q. Okay? This is going to have to be the factors here of -1, okay, of our constant term, and we'll have to divide that by the factors of our leading term, the factors of the coefficient of the leading term. Okay. All right. So now to deal with this negative, let's just pull the plus or minus out here. Okay. Well, the factors of 1 is really nice. It's just 1 in itself, so we don't have much there. The factors of 4, on the other hand, are 1, 4, and 2 times 2. So this is equal to plus or minus 1, plus or minus 1/2, and plus or minus 1/4. Okay, so in this situation, this is all of the possible zeros, rational zeros. Because it could have irrational zeros, and it could have imaginary zeros or complex zeros, and we wouldn't know directly from here. Okay. All right. Now we need to test. There's 6 of them. Okay. I want to start with the easiest one first. Okay. So let's start with x equals positive 1, okay, and put this through long division. Now remember, with this, in long division, we'll take the coefficients. So this is from the x cubed. There is no x squared term, so we have to put that 0 in. And then minus 3 and minus 1. Okay. Now let's do the long division. We bring down the, or not the long division, the synthetic. 4 comes down. 4 times 1 is 4. Okay. Now we add 0 plus 4 is 4. 4 times 1 is 4. Now we add -3 plus 4 is 1. 1 times 1 is 1. And -1 plus 1 is 0. Okay. Remember, this last one is the remainder. Okay. So what this means then is that x minus 1 is a factor of f of x. Okay. Because the remainder is 0. So we could rewrite the equation up here equal to 0 as x minus 1, and now this is going to be the quotient, okay, the coefficients, okay? So it wasn't x cubed, so this will become an x squared. So 4x squared, this is positive, plus 4x, plus 1. Okay, now that equals 0. Now I can continue to run through all of these and redo long division with this, with the new ones. However, this is quadratic, and so we know we can solve it. And I highly doubt, well, let's see if it'll factor x minus 1. Okay, so 1 is a perfect square, and this is a perfect square. So let's try 2x and 1 and see if this works. Okay. So this would be 4x squared plus 2x plus another 2x is plus 4x plus 1. Okay. So great, that worked. Okay. Now we can solve this. So it's either that x minus 1 equals 0, or 2x plus 1 equals 0, or again 2x plus 1 equals 0. Okay. So here we have x is equal to 1, and so that means x minus 1 is a factor, right? Or 2x is equal to negative 1, so x is equal to negative 1/2. Okay. So that would mean x plus 1/2 is a factor. Okay. And here also we'll get negative 1/2. Remember, this is a repeated root or solution for 0. Okay. So I hope this makes sense about now how creating this list of these factors, these possible zeros, and you pick some. Now if 1 hadn't worked, we'd moved on to negative 1. And then positive 1/2 and negative 1/2 and so on and so on. So we hope to find 1, and then that will leave us with a quotient that is easily factorable, or possibly we have to use the quadratic equation. Let's talk about the fundamental theorem of algebra then. Okay. So we have the fundamental theorem. I'll spell it out here. Theorem of algebra. Okay. So let's say if our function is a polynomial, and the degree has to be greater than 0. Okay, otherwise it's just a constant. Then what we can say is that the function has at least one complex 0. So at least one complex number, one solution will be a complex number. Well, we can just look back at this and say, what the heck are you talking about? Right? Here we had x equals 1 and negative 1/2 and negative 1/2. These aren't complex numbers. These are real numbers. Okay, so let's just go back and remember what's happening in the number systems. First we have the natural numbers. Then we added 0, so the wholes were there. Then we added the fractions, so these are the rationals. Okay, this is the group that the rational zeros theorem is talking about, is these 3. Then off to the side we have these other numbers, the irrationals, right? The square roots of 2 and such. Okay. Now when you put all this together, this made the real numbers. Sorry, let me write it in here. The real numbers. Okay, so this is the real numbers. But then remember, we expanded it because we could add on these imaginary numbers. Okay, they're off to the side, but that's where we get the i's. Okay. And when you take these all together, this whole box, this forms the complex. So it could be our complex number, like we had when we said x is equal to 1. Remember that all complex numbers are written in form a plus bi. So we could just write this solution as x is equal to 1 plus 0 I. Okay. Now we generally don't, but we could. Okay, so this is what the fundamental theorem is showing. So let's do another example where we try and find these. Okay, so for example, let's find the zeros 3x cubed plus 9x plus x plus 3. Okay, so now let's begin. Okay, so we know this. X will be equal to some p over q, some rational. Okay, where the first one is the factors of 3 from here, okay, this one, and the bottom is also the factors of 3, but now we're using this 3, okay, and it's the division of the 2, so this is equal to plus or minus the set. The factors of 3 are 1 and 3. The division of those. So our possible sets here are dividing by 1 first of all, plus or minus 1, or plus or minus 3. Now dividing by 3, plus or minus 1/3, or plus or minus 3 over 3, which is 1, which are already represented. Okay. So these are our possible rational zeros. Alright. So again, let's start with the easiest one first. Let's go by -1, or +1, sorry. You can go by -1, it doesn't matter. Okay, so 3, oh, this should be x squared. 3, 9, 1, and 3, all positive. And now we do the synthetic division. You bring the 3 down. 3 times 1 is 3. Then we add 9 plus 3 is 12. 12 times 1 is 12. 1 times 12 is 13. 13 times 1 is 13. So this remainder is not 0. Okay. We don't even care what the remainder is. Alright, let's try -1. 3, 9, 1, 3. Okay. Bring down the 3. 3 times -1 is -3. 9 minus 3 is 6. 6 times -1 is -6. 1 minus 6 is -5. -5 and plus times -1 is +5. So our remainder here is 8. Again, so that's not a 0. Alright, so now let's move on to +3. Okay. 3, 9, 1, 3. Bring the 3 down. 3 times 3 is 9. 9 plus 9 is 18. 18 and 3 is 54. Yeah. 54 and 1 is 55. 55 times 3, well, it doesn't matter. That's not going to be 0. Okay. So now we move on to the next one, -3. 3, 9, 1, 3. Bring down the 3. 3 times -3 is -9. 9 minus 9 is 0. 0 times -3 is 0. 1 plus 0 is 1. 1 times -3 is -3. And here we found a factor. Okay. So what that means is that our function, okay, 3x squared, cubed, plus 9x squared, plus x plus 3, if we were looking for solving it for zeros, what we have then is that x plus 3, okay, because minus 3 is the solution, times, now this will be 3, 1 less than this degree, x squared, plus 0x, plus 1 equals 0. So now we can find the other solutions very easily. Now, if you split it back up, you'll get x plus 3 equals 0, or 3x squared plus 1 equals 0. We know this, x is equal to negative 3. We saw that up here. Now this is quadratic, so we can solve it. So this is 3x squared is equal to negative 1, or that x squared is equal to negative 1/3, so that x must be equal to plus or minus the square root of negative 1/3. Negative. And when we take the square root of a negative number, then we'll see here, x is equal to plus or minus I times the square root of 1/3. And let's rationalize this while we're at it. Plus or minus I, this is the same thing as root 1 over root 3. Okay, the I times that. Okay, over root 3. Okay. And then to rationalize, we multiply it by square roots of 3. So this is plus or minus I roots of 3 over 3. Okay. So in this case, we did get 3 solutions. 2 of them are complex. Okay. The positive I root 3 over 3 and the negative I root 3 over 3. And this will always happen. These are the complex will always come in pairs. So, okay. So let me show you that. And interestingly, what we should make note of, if you were to graph this function, then we only have one real solution at x equals negative 3. And when it gets graphed, then what it looks like is this. Okay, we have a positive odd degree, so the end behavior is like this. The multiplicity of this 0, remember this is negative 3, 0, is 1, so it will cross here. Okay, and then there are no other solutions because the other two are complex. Okay, let's do another one. F of x is equal to 2x cubed plus 5x squared minus 11x plus 4. Okay, we want to find the zeros. Okay, so that means we're solving 2x cubed plus 5x squared minus 11x plus 4 is equal to 0. So let's find our possible rational solutions. Let's see, P over Q. It's going to be plus or minus a set of. So P has to be the factors of 4. And our denominator Q will be the factors of 2. Okay. Well, the factors of 2 are just 1 and 2. Plus or minus. And the factors of 4 are 1, 2, and 4. Okay. So simplifying this, then this becomes plus or minus 1, 2, 4. Oops, now I can't write it like this. I have to put the set notation if I'm going to do that, or I have to put the plus or minus in front of everything. 1/2, 2 over 1 is 1, and 4 over 2 is 2. Okay, so plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. Okay, I really don't have an idea where this one falls, so let's just start with the easy one. Okay, 1, 2, 5, negative 11, 4. Bring the 2 down. 2 times 1 is 2. 5 and 2 are 7. 7 and 1 are 7. Negative 11 plus 7 is negative 4. Negative 4 times 1. Oh, thank goodness. Woohoo! It's the first one we tried. Okay. So that means we can rewrite this. This will say that x minus 1 is a factor. And here will be our quotient. This is a cube, so this will be squared. 2x squared plus 7 x minus 4 equals 0. So then it's either that x minus 1 equals 0 or 2x squared plus 7x minus 4 equals 0. So x is equal to 1. I'll do the easy one. This is not going to factor, and I certainly don't want to complete the square. Once I divide by 2, I'm going to have 7 halves there. So let's just use quadratic. Okay, so x is equal to negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a. Now simplifying, negative 7 plus or minus the square root of 49. 4 and 2 are 8. 8 and 4 are 32. And then looking at the signs, positive and, let's see here, negative and negative will become positive over 4. Is that right? Negative b plus or minus b squared minus 4 times a times c. And this is 2x squared plus 7 minus 4. Okay, I think so. So x is equal to negative 7 plus or minus the square root. 49 and 32 is 11. 81. Oh my gosh, this thing probably was going to factor. Let's see. Which is equal to negative 7 plus or minus 9 over 4. Okay, so it's either that x is equal to negative 7 plus 9 over 4 or negative 7 minus 9 over 4. So 9 minus 7 is 2 over 4, which is 1/2. Okay, so that was one of ours. And this is negative 16 over 4, which is negative 4. Okay, so actually these were both of our choices. And I guess this means this would have factored then. I guess that factors into, let's do it over here. Well, here, let me show you. Okay. Here we have that x is equal to 1/2 is a 0, or that x minus 4 is a 0. Okay. So what that means is if I backtrack this, I could add 4 to both sides. So that would mean x plus 4 equals 0. Let's multiply this by 2, so we get 2x equals 1. If I subtract 1, then that would have happened. Okay. And so 2x minus 1 times x plus 4 was equal to 0. Then if we multiply these together, just this part, we'll see that that's how they factor. Plus 8x minus 1. Yep, it was going to factor. So, and this is, we should really bring that down just to stay copacetic, but, because we were splitting it. Okay, so that one didn't have any complex roots. But let me tell you about the complex roots. Okay, before we move on, and then I'll show you the last bit that we have here. So we have this complex conjugates theorem. Okay. Yet another one. So let's say we have some function, and we can write it as x minus c1, the first complex root, and x minus c2, the second complex root, and we have as many roots as we need. We'll say n roots of them. Okay. Now remember, this could be x minus 1 or x minus 3 because the complex encompasses the real numbers. Okay. But if you get a if these c's if the c's are in the form if any c, okay, let's be clear about that, if any c is in the form a plus bi, the way we're used to traditionally talking about complex zeros, then in the form, then a minus bi will also be a root. And we can just look at that from a very basic example. Okay, x squared plus 1. Okay, if we solve this, if you use the possible rational theorem, then you would get plus or minus the set of 1 over 1, so you really only have plus or minus 1 to test from. Okay. Now, we don't have to do this because it's quadratic. So we'd see x squared is equal to negative 1, so x must be equal to plus or minus the square root of negative 1, and here's where the conjugacy comes in, okay, which is plus or minus I. Okay. So I had something in the form a plus bi, this is just 0 plus 1i, or 0 minus 1i, okay, but they're both there, and so this will always happen. Okay, so how is this helpful? Well, let's say we had to create a polynomial. This is something I was doing over here when I was looking at the zeros. So let me give you a shorter example before we do this again. Okay, let's take one that we know factors very easily. So if we have x squared minus 5x plus 6, okay? Okay. Okay. And we're trying to set this equal to 0. Then we know that this factors into x. Actually, this one is going to factor into x minus 3x minus 2, right? Minus 3x minus 5 plus 6, okay? Then when we're finding the solutions, we break it apart. We say x minus 3 equals 0, or x minus 2 equals 0, and from there we can solve x is equal to 3, or x is equal to 2. Okay? So that means if I just knew what the solutions were, what I was trying to do before is backtrack. Well, what would this, if this is a solution, then if I subtract 2 from here, I get it equal to 0. If I subtracted 3, I would have it equal to 0. Then these two would have been factored together to equal 0. And then I could have recreated the original function. Okay. So let's do something like that. Let's say that we need a 4th degree polynomial whose solutions are x is equal to negative 3, negative 2, and I. Okay, so x minus 3 equals minus 3, x equals minus 2, x is equal to I. But remember, if we have I, we also have x is equal to negative I. Okay. Which means if negative 3 is a 0, x plus 3 is a factor of the polynomial, x plus 2 is a factor of the polynomial, x minus I is a factor of the polynomial, and x plus I is a factor of the polynomial. Okay. So our polynomial, okay, is going to be equal to the multiplication of these 4 things. Okay. Now let's handle the complex numbers first. Okay, let's FOIL these. Okay. So when we FOIL this, we'll get x times x is x squared, plus an I minus an I. Well, those go away. And then minus I squared. But remember, I squared is negative 1. So when you multiply these two together, you're actually multiplying x squared plus 1. Which we knew. We saw that earlier. Okay. Alright, now we still have to multiply by these two. So let's see what happens when we multiply them together. Okay, so multiplying these two together, we'll get x squared plus 2x plus 3x is plus 5x plus 6. Okay. And these have to be multiplied together. Okay, remember when you're multiplying polynomials, you want to, so let me rewrite this so it just looks a little bit better. Okay, let's put the smaller one, let's just commute these x squared plus 1 and x squared 5x plus 6. Okay, when multiplying polynomials, you'll have to take the first and distribute it through everything. Okay, so that gets us x to the 4th plus 5x cubed plus 6x squared. We need a little equal sign in here. Then I have to take this one through. 1 times anything is itself. So plus x squared plus 5x plus 6. So in the end, the polynomial, a 4th degree polynomial that has these roots, are x to the 4th plus 5x cubed plus 7x squared, combining these, plus 5x plus 6. Okay, so I think that should get you through your homework. If you need to create the polynomial, work backwards from your zeros. Remember the solutions. Okay, if this is the solution, then the opposite sign becomes the factor. That's from our factorization theorem. Okay. Also remember that conjugate pairs will come, complex numbers will come in conjugate pairs. And let's see, your possible rational zeros. Yes, remember the rational zeros theorem. If this is a polynomial and it has a rational zero, okay, that is, it can be written as a fraction, it's the factors of the constant over the factors of the leading coefficient. And the other big theorem, let's see, that we did talk about, if p of x is a polynomial and it's divided by x minus c, then you can always check what the remainder is by plugging in that constant. If it equals 0, then it's a factor, but it won't tell us what the quotient is. So we'll have to keep going if we're looking for all the zeros. Okay, send me an email if you have a question.